Physics works. Everywhere. Always. That is not optimism, it is the observed record across 14 billion years, tested across scales from the interior of a proton to the threads connecting galaxy superclusters. The equations hold. The predictions confirm. The universe, as far as we have been able to measure it, obeys. This coherence is not assumed. It is continuously verified by independent instruments on different continents, by different teams operating under different theoretical frameworks across different wavelengths and different energy regimes. When all of them agree, we call that agreement a law of physics. It is the most reliable thing our species has ever produced. There are 7 places in the universe, or conditions within it, where that coherence breaks. Not entirely. Not catastrophically. The equations still function as working approximations. But when precision matters, when the sharpest predictions of our best models are tested against the sharpest measurements we have ever taken, they return numbers that do not agree with what is observed. In some cases, the discrepancy is a factor of 2. In others, it exceeds 5 standard deviations, the threshold scientists use to declare a result confirmed rather than a fluctuation. In one case, the discrepancy operates not at the level of a single measurement or a single object, but at the level of the assumption that makes all cosmological measurement coherent in the first place. These are not theorized gaps. These are observed ones. The data is real. The instruments have been independently verified. The analyses have been repeated by different teams with different methodologies. The explanations remain absent. What follows is documentation. There is a recipe for the early universe, and it is precise. In the first 3 minutes after the Big Bang, when temperatures still exceeded 10 billion degrees, protons and neutrons fused to produce the lightest atomic nuclei, hydrogen, helium, and trace quantities of lithium. This process, Big Bang nucleosynthesis, abbreviated BBN, is one of the most rigorously tested frameworks in all of cosmology. The predicted elemental abundances, derived from the baryon density imprinted in the cosmic microwave background, agree with observations of deuterium and helium-4 to within. Measurement uncertainties of a few percent. Those are not rough estimates. They are precise agreements between a calculation made on paper and a measurement taken in the light of the universe itself. For 2 of the 3 lightest primordial elements, the theory and reality are an independent, repeatedly confirmed agreement. BBN works. The oldest stars in our galaxy are the closest surviving record of that primordial chemistry. Population 2 stars, metal-poor halo stars, formed in the earliest epoch of galactic assembly, before successive stellar generations seeded the interstellar medium with heavier elements, preserve in their outer layers the chemical inventory of the gas from which they condensed. That gas was not processed through the nuclear burning that produces heavier elements inside later stars. It carries, in principle, the ratio of elements the Big Bang actually forged. Beginning in the 1980s, high-resolution spectroscopy at the Very Large Telescope, the Keck Observatory, and the Hubble Space Telescope began measuring the lithium content of hundreds of these ancient halo stars across independent surveys spanning 4 decades. What accumulated across that time, from multiple instruments and multiple research groups with no coordinated agenda, is what cosmologists now identify by a quiet and clinically exact designation, the primordial shortfall. The oldest stars in our galaxy contain exactly 1/3 the lithium the Big Bang should have produced. Big Bang nucleosynthesis, constrained by CMB baryon density measurements, predicts a primordial lithium to hydrogen ratio of 4.94.72. 10. The Spite Plateau, the measured lithium abundance consistently observed across metal-poor halo stars, named for the pair of astronomers who first identified the pattern, sits at 1.6, 0.3, 10. The discrepancy is a factor of approximately 3, Not 3%. Not 30%. A factor of 3. This gap has been reproduced across surveys spanning different stellar temperatures, different metallicities, different galactic positions, and multiple generations of instruments operating across different decades. The plateau is not a single contested measurement subject to future revision. It is a pattern locked across hundreds of independent stellar spectra, each measured separately, each returning the same ratio. The universe forged lithium in the first minutes of its existence. The oldest stars do not carry it. And every old star tested returns the same amount of missing. Imagine baking bread using a recipe that has been validated thousands of times, one that produces a fixed ratio of ingredients in every loaf, in every oven, in every kitchen. Tested. Then retrieve the oldest loaves, the original batch, unmixed with any later ingredient, and find that a specific component is absent in a fixed proportion across every oldest. Sample, regardless of which bakery you examine. The first explanation is stellar depletion. The lithium was produced by the Big Bang, but subsequently destroyed by nuclear reactions occurring beneath the visible stellar surface, in convective layers that circulate material into hotter interior regions where lithium nuclei are consumed. This hypothesis has been modeled extensively. It fails on a specific observational fact, the uniformity of the spike plateau itself. Convective mixing and diffusion operate at rates that depend on stellar mass, temperature, and age. Different stars with different physical parameters should show different depletion rates, producing a measurable spread of lithium values across the survey population. The spike plateau shows no such spread. The dispersion across hundreds of halo stars is too small, too consistent, too flat to accommodate the range of depletion rates that the required mixing models predict. The mechanism that should explain the deficit simultaneously predicts a variation that the data refuses to show. The second explanation modifies Bibbon itself, adjusting nuclear reaction rates in the early universe or introducing non-standard conditions to produce less primordial lithium than standard calculations yield. This fails because Bibbon is a coupled system. The physical conditions governing lithium production also govern deuterium and helium-4 through the same nuclear pathways. Every modification large enough to reduce primordial lithium by a factor of 3 simultaneously shifts deuterium or helium-4 predictions outside the boundaries of what current measurements allow. Deuterium abundance, measured in quasar absorption spectra, is constrained to a precision of a few percent. Helium-4 mass fraction is measured in metal-poor extragalactic H2 regions with comparable precision. Those constraints are simultaneous and mutually exclusive with any modification that resolves the lithium deficit. The coupled system leaves no available room. A third approach proposes inhomogeneous BBN, baryon density varied spatially across the early universe, with our halo stars preferentially drawn from regions where lithium production was suppressed. This cannot explain the spike plateau. A baryon density variation large enough to suppress lithium by a factor of 3 would produce a distribution of lithium abundances across the stellar population formed from those varied regions. The plateau is not a distribution. It is flat. The very uniformity that makes the problem reproducible across every instrument and every survey is precisely what rules out spatial variation as an answer. If no depletion mechanism produces the plateau's uniformity and no modification to Ben resolves the deficit without breaking the deuterium and helium constraints, then either the physics governing the universe's first 3 minutes is incomplete in a way not yet identified, or ancient stars erase light elements through a mechanism that no current model of stellar physics contains. The lithium problem lives in objects with coordinates, specific stars, distributed across the galactic halo, measured 1 spectrum at a time. What we turn to next also has a coordinate, a fixed point above the Antarctic ice. But the objects that instrument detected did not originate there. They arrived from somewhere outside our standard model of particle physics, having traveled through thousands of kilometers of solid rock without the interaction, the equations. Demand. The category of violation changes. The scale contracts to a single point, then opens into a direction the physics refuses to follow. The standard model of particle physics is the most precisely tested theory in the history of science. Its predictions for how particles interact, how they scatter, how they are absorbed, what energies they can carry across different materials have been confirmed to precisions. Better than 1 part in 10 billion in some regimes. Among its most reliable predictions is this: at sufficiently high energies, a neutrino cannot pass through the Earth. The interaction cross-section increases with energy, and above certain thresholds, even the neutrino, which passes through light years of ordinary matter at low energies without stopping, becomes effectively opaque to thousands of kilometers of solid rock. The Earth is impenetrable to particles at those energies and those angles. That is not a simplification. It is a calculated, verified, experimentally confirmed result from laboratory measurements of neutrino cross-sections across multiple accelerator experiments. The Antarctic Impulsive Transient Antenna, ANITA, is a NASA balloon-borne radio antenna array that circles the Antarctic continent at altitude designed to detect incoming cosmic neutrinos arriving from above and striking the ice below. During its first flight in 2006 and its third flight in 2014, ANITA detected something its engineering specifications did not anticipate: 2 radio pulses arriving from below the horizon, from the direction of the Earth's interior, with characteristics that the most straightforward physical explanations cannot resolve. The ANITA team spent years applying every available systematic check to these events. The results acquired, after that process, a designation the collaboration uses with the measured precision of people who have run out of alternatives: upward defiance. 2 events, both upward, neither explained. The first event, detected during ANITA the 1st in 2006, and the second, during ANITA the 3 in 2014, radio pulses with steep upward trajectories implying origin from tens of degrees. Below the horizon, carrying estimated energies of approximately 0.6 and 0.56 exaelectronvolts respectively. At those energies and angles, the interaction length of a standard tau neutrino inside Earth is short enough that the predicted flux for upward-going events approaches 0. The Earth's opacity at those energies is not a soft limit. It is a near absolute one. Both events showed polarity characteristics that, in the simplest subsurface ice reflection model, require Fern layer configurations absent from the broader ANITA dataset across. Thousands of other candidate events from multiple flights. The Pierre Auger Observatory, the world's largest cosmic ray detector, spanning 3,000 square kilometers of Argentinian plains, subsequently examined the sky directions, consistent with the event's implied source regions. Its 2025 analysis, published in Physical Review Letters, Volume 134, page 121003, set upper limits on any particle flux-producing events of this type that are difficult to reconcile with a source population large enough to generate 2 detections at the observed rate within the expected solid angle and exposure. Imagine shining a flashlight at a thick concrete wall, a wall whose composition and thickness have been measured precisely, confirmed to absorb or scatter every photon that strikes it. Then watch a clean beam emerge from the other side, in a single specific location, as though the concrete between source and beam contained a passage the measurements cannot find. The first explanation is subsurface ice reflection. Density inversions in the Antarctic ice sheet's Fern layer, compressed snow just below the surface, could in principle produce radio wave reflections without the polarity inversion expected from clean surface reflections. This mechanism exists in some geometric configurations. It fails to generalize to these events. The specific angles, energies, and polarization characteristics of both ANITA events require Fern layer configurations not observed across the broader ANITA dataset, which records thousands of candidate events across multiple flights and survey regions. If Fern layer reflection were responsible, similar events should appear throughout the ANITA data stream. They do not. The mechanism requires the same unlikely geometric coincidence twice, across two separate flights years apart, without producing an analogous population elsewhere in the dataset. The second explanation invokes beyond standard model particles, sterile neutrinos, tau leptons with anomalous decay properties, or other exotic species with reduced interaction, cross-sections capable of traversing thousands of kilometers of rock. Every mechanism of this type has been constrained from multiple independent directions. IceCube, the cubic kilometer neutrino detector embedded in Antarctic ice at the South Pole, has not detected a diffuse background of events at the energies and flux rates, implied by two ANITA detections within the relevant solid angle and exposure time. The Pierre Auger Observatory's 2025 upper limits on the implied particle flux rule out or heavily suppress the populations required by most proposed exotic models. Wissel et al. 2025 have explored the remaining parameter space for beyond standard model interpretations and found no unconstrained region that simultaneously fits both events while satisfying the Auger and IceCube non-detections. The parameter space is closed. A third explanation attributes the events to instrumental artifacts or anthropogenic radio backgrounds from human activity on the Antarctic ice. The event's directionality, energy characteristics, and timing are inconsistent with ground-based interference patterns identified in the ANITA calibration and systematic analysis. Both events survive the collaboration's dedicated exclusion of identifiable terrestrial sources. The instrument did not generate them. There may exist pathways through ordinary matter or particle species capable of traveling them that the standard model does not contain at energies above a certain threshold. Both events point in a direction the equations refuse to follow. What was just described operated at the scale of Earth's interior, two discrete signals, detected at a single Antarctic point, implying particles that crossed our planet. Through pathways the standard model does not recognize. What follows operates at a fundamentally larger scale, the full volume of the observable universe populated by particles arriving from unknown distances with energies so extreme that the fabric of space itself should have stopped them before they reached us. The category of physics challenged is not particle interaction inside a planet. It is the boundary that separates the observable universe from what lies beyond our horizon. There is a hard limit on how far certain particles can travel across the universe, and it is a physical consequence of the most abundant radiation field in existence. The cosmic microwave background, the diffuse afterglow of the Big Bang, filling all of space at a temperature of 2.7 Kelvin, is not empty. It contains approximately 411 photons per cubic centimeter throughout the entire observable universe. When a proton traveling at near the speed of light collides with one of those photons at high enough energy, the interaction produces pions and saps the proton's kinetic energy. This loss accumulates across distance. A proton carrying more than approximately 510 electron volts, 50 exeelectron volts, loses energy so rapidly through repeated CMB photon interactions that it cannot travel more than roughly 100 to 200 megaparsecs before dropping below that threshold. This is the Greisen-Zatsepin-Kuzmin cutoff, the GGK limit. It defines a hard propagation horizon. Particles above GGK energy can only originate within a specific maximum distance. That distance, in cosmological terms, is very small. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah are the two largest dedicated instruments for detecting ultra-high energy cosmic rays, particles. arriving from outside the solar system at extreme energies. Both have recorded events at and above the JWST energy threshold from arrival directions distributed across the full sky. In 2021, the telescope array detected a particle whose energy analysis, completed and published in 2023, returned a value of approximately 2.410 electron volts, more than 40 times the energy of the most powerful particles ever produced in a human accelerator. The collaboration searched the sky around its arrival direction for a source within the maximum propagation distance that JWST physics allows. The result of that search is what the field now refers to with an understated precision as trans-cutoff persistence. Nothing within 100 megaparsecs of the arrival direction. The JWST cutoff sits at approximately 5 to 610 eV, with a predicted sharp suppression in cosmic ray flux above that energy. Observed individual events at 10 eV, with the Amaterasu particle at 2.410 eV, roughly 5 times the nominal cutoff. Hundreds of events above the threshold have been recorded across combined auger and telescope array datasets. Within the JWST propagation horizon of approximately 100 megaparsecs in the Amaterasu particle's arrival direction, all sky surveys across radio, optical, X-ray, and gamma ray. Wavelengths find no galaxy, no active galactic nucleus, no compact object with the properties required to accelerate particles to 2.410 eV using any known mechanism. The nearest plausible source candidates lie beyond the propagation limit that the physics explicitly forbids. The particle arrived from a direction where the universe is quiet. It arrived intact. Imagine throwing a snowball across a field warm enough to dissolve it long before the far side, a field whose temperature and humidity have been precisely measured along the entire path. Then watch a specific snowball arrive at the far boundary, cold and intact, from a direction where the field is empty, as though it crossed conditions different from the ones you measured. The first explanation is heavy nuclear composition. Heavier nuclei, iron or intermediate mass elements, have different interaction thresholds with CMB photons, allowing them to travel somewhat farther than protons at comparable energies. This partially accommodates the aggregate spectrum shape. It fails to resolve the Amaterasu event, specifically composition measurements from the Auger Observatory derived from air shower muon content and fluorescence profiles indicate a mixed and not predominantly iron composition at the highest energies. Even assuming an iron nucleus at 2.410 eV, no counterpart source has been identified within the extended propagation distance that heavy nuclei would allow. The composition argument shifts the threshold. It does not produce a source. The second explanation invokes Lorentz invariance violation, modifications to the standard relativistic relationship between energy and momentum at extreme energies, which could alter or eliminate the JWST interaction for certain particle species. This has been explored across multiple theoretical frameworks. It fails to produce a consistent fit to the full observed spectrum and arrival direction distribution simultaneously, and is constrained by TV gamma ray observations of distant blazars, which confirm that standard photon propagation and pair production physics hold across the relevant energy and distance ranges. The departure from Lorentz invariance required to suppress JWST losses is ruled out by independent astrophysical observations. The third explanation proposes undiscovered local sources, nearby accelerators operating in wavelengths not captured by current electromagnetic surveys. This is constrained by multi-messenger follow-up. The Amaterasu arrival direction has been examined for neutrino counterparts by IceCube, for gamma-ray counterparts by the Fermi Large Area Telescope, and for radio and optical counterparts by multiple survey programs. No source has been identified within 100 megaparsecs of its arrival direction with the energy output and geometry required to produce the event. The sky is quiet. No mechanism is identified. Our models of particle propagation across intergalactic space miss an entire regime of extremity that is physically occurring in the universe right now. Particles arriving here from distances and sources that the standard propagation physics explicitly forbids. The previous three entries had coordinates fixed to physical objects and detection sites: stars in the galactic halo, a balloon above Antarctic ice, particle arrival directions across the full sky. What follows also has coordinates, specific redshifts spectroscopically confirmed, fixed to galaxies that existed when the universe was a small fraction of its current age. But the violation is not in how particles travel. It is in whether structures as large and organized as galaxies had enough time to form at all. The objects exist. The physics of their formation does not accommodate them. The standard cosmological model describes how structure formed after the Big Bang with considerable precision. Following recombination, when the universe cooled enough for neutral hydrogen to form, approximately 380,000 years after the Big Bang, the first seeds of cosmic structure were tiny density fluctuations in the primordial plasma confirmed in the cosmic microwave background and measured to extraordinary precision by the Planck satellite. Gravity amplified those fluctuations through a process called hierarchical assembly. Small clumps of dark matter formed first, then merged over hundreds of millions of years into larger halos, which gradually accumulated enough gas to form stars, then stellar populations, then galaxies. The timeline of this assembly is not a free parameter. It is constrained by the CMB power spectrum, by large-scale structure surveys, by the observed merger histories of galaxies across cosmic time, and by the baryon density of the universe. Standard lambda CDM cosmology produces a specific, falsifiable prediction: massive, well-organized galaxies containing more than 10 billion solar masses of stars required. Several billion years of hierarchical growth to build. They should not exist in significant numbers when the universe was less than 1 billion years old. In July 2022, the James Webb Space Telescope transmitted its first deep-field observations of the early universe. By early 2023, multiple independent research groups had identified a population of galaxy candidates at redshifts above 7, corresponding to epochs when the universe was less than 800 million years old, with estimated stellar masses in a range that the lambda CDM formation framework had not predicted and could not immediately accommodate. These were not individual outliers subject to measurement uncertainty. They were an ensemble. The pattern they constituted was, to use the term that appeared in peer-reviewed analysis without editorial softening, structurally impossible within the standard formation. Timeline. Galaxies the size of the Milky Way existed when the universe was less than 700 million years old. In a paper published in Nature in 2023, volume 616, pages 266-269, lab and collaborators identified 6 candidate massive galaxies at redshifts between 7.4 and 9. 1. With combined stellar mass estimates implying a stellar mass density at those epochs roughly 100 times higher than lambda CDM predicts for galaxies of that mass at that era. One candidate carried a photometric stellar mass estimate exceeding 10 solar masses, equivalent in stellar content to the Milky Way at a cosmic age of less than 700 million years. Independent analysis by Boylan-Colchin 2023, Nature Astronomy applied a specific constraint for each massive candidate. He calculated the total matter, dark and baryonic, available within the causal volume that could have contributed to that galaxy's formation by that epoch, assuming the most optimistic possible star formation efficiency. For several candidates, the estimated stellar mass exceeded what could be produced even if 100% of all available baryons within the entire contributing volume had been converted into stars. Real galaxies convert a few percent of their baryons into stars under typical conditions. 100% is not an upper bound that better models can approach. It is a physical ceiling that cannot be crossed. Spectroscopic confirmations, including Curtis Lake et al. 2023. Nature Astronomy, confirming galaxies at Z Discoverer 10.3, 11.4, 12.3, and 13.2 have placed multiple objects beyond photometric uncertainty. The galaxy Jade's GS-Z14-0, spectroscopically confirmed at Z-SCUV 1432, existed approximately 290 million years after the Big Bang and already carries a stellar mass and physical size inconsistent with a system just beginning its formation history. Imagine watching a building under construction and calculating, from the observed delivery rate of materials and the known size of the construction crew, the earliest possible completion date. Then drive past the site on day 3 and find the building fully furnished, occupied, and with established gardens, as though the materials arrived and assembled before thee. Construction schedule began. The first explanation proposes higher star formation efficiency in the early universe, the conditions of the early cosmos, higher gas densities, lower metallicity, different. Feedback mechanisms may have allowed young galaxies to convert gas to stars faster and more completely than galaxies do today. This can reduce the tension for less extreme cases. It cannot eliminate it. For several of the most massive candidates, efficiency would need to approach or exceed physical limits that no known stellar process achieves under any conditions. And efficiency alone does not account for the structural regularity observed. Multiple high redshift dust objects show organized disk morphologies and established stellar populations, not the irregular star-forming clumps that a model of extremely rapid early assembly would produce. The second explanation attributes the photometric mass estimates to systematic bias, strong emission lines from active star-forming regions, or ANG contaminating the rest frame. Optical photometry used to infer stellar mass, artificially inflating estimates. This is a legitimate avenue of ongoing scrutiny. Spectroscopic follow-up on confirmed objects has not eliminated the mass excess in individually verified cases. The ensemble of high redshift JWST galaxies is too large, and their excess brightness too consistent across multiple independent analyses using different instrument modes and data reduction pipelines, to be entirely explained by photometric systematics. The excess of bright objects at high redshift persists after every correction applied. A third explanation modifies early universe physics directly. Adjusted primordial power spectra, warm dark matter variants, or modified gravity on small scales. Each such modification must simultaneously preserve the CMB acoustic peak structure, the observed baryon acoustic oscillation signal in large-scale galaxy surveys, and the supernova Hubble diagram, all of which confirm standard lambda CDM2 within tight bounds. No proposed modification resolves the JWST excess without creating new discrepancies in at least one of those independent confirmations. The universe was building structures it did not yet have the time, the matter, or the available physics to build, and the number of confirmed examples increases with every new JWST observing cycle. Everything before this was a puzzle, a missing element, an upward signal, particles surviving where they should not. Galaxies assembled before the model permits, each one bounded, a specific observation that does not agree with a specific prediction. What follows is not that kind of puzzle. It is a place where the equations agree with themselves, where every framework correctly predicts what must exist inside the densest objects in the universe, and the universe refuses to confirm it. There is no solution date. There is only the gap between what the math demands and what the matter inside those objects permits to exist. The physics of matter under extreme compression is among the best tested domains in nuclear science. As density increases beyond the threshold of atomic nuclei, as protons and neutrons are pressed closer under gravitational force, the strong nuclear interaction governs which phases of matter become energetically stable. At densities 2 to 3 times the nuclear saturation density, which is approximately 2.810 grams per cubic centimeter, the energy cost of producing strange quarks falls low enough that baryons containing strange quarks become thermodynamically favored. These particles, hyperons including lambda, sigma, and Xi particles, are predicted to appear inside dense matter not as a speculative possibility, but as a consequence of the same strong force physics confirmed in particle accelerator experiments across decades. The prediction is not ambiguous. It is not model-dependent in a way that allows easy escape. Hyperons must appear in sufficiently dense matter. The physics demands them. The densest stable objects in the known universe are neutron stars, the collapsed remnants of massive stellar explosions, compressing roughly 1.4 to 2 solar masses of matter into a sphere approximately 12 kilometers across. Their interiors, which reach densities 2 to 8 times the nuclear saturation density, are the only place in the observable universe where the Hyperon prediction can be directly tested. The NICER telescope, NASA's neutron star interior composition explorer, mounted on the International Space Station since 2017, measures neutron star masses and radii through X ray pulse timing with precision not previously achievable for these objects. What NICER and radio pulsar timing have returned is a result the field describes, without overstatement, as an inconvenient constraint. The densest matter we can observe refuses to soften the way our physics of that matter requires. Neutron star equation of state models that correctly incorporate hyperon formation predict a maximum sustainable mass of approximately 1.4 to 1.6 solar masses. Beyond that threshold, hyperon softening collapses the internal pressure support, and the star cannot hold itself against gravity. Observed. PSR J0740 plus 6620. Measured at 2.08 0.07 solar masses via Shapiro delay radio timing, et al. 2021, and confirmed by NICER X-ray analysis, which also constrains its radius to 12.39 plus 1.30/0. 98 kilometers Riley, et al. 22-1, Sergio 9520607, measured at 2.35.17 solar masses, Roman et al. 22-2. The gravitational wave event GW170817, a neutron star merger detected by LIGO and Virgo, constrains the tidal deformability of neutron stars 800, independently anchoring the equation of state to a regime that is stiff, that resists compression far beyond what any hyperon-inclusive model allows. The most massive neutron stars observed exceed the maximum mass predicted by any equation of state that includes hyperons by approximately 0.5 to 0.9 solar masses. The discrepancy is not in the measurement. It is in the matter. Press your palm against a surface that, by everything known about its composition, should compress and yield. It does not yield. It holds. The material behaves as though it does not contain the component that physics says it must contain. Yet removing that component from the physics produces predictions that fail. Elsewhere, the first proposed resolution is the repulsive three-body hyperon interaction. If the force between multiple hyperons in dense matter is sufficiently repulsive, it could stiffen the equation of state enough to restore the 2 solar mass ceiling even with hyperons present. This has been modeled extensively. The specific problem is calibration. Three-body hyperon interactions cannot be measured in any current laboratory experiment because the densities required do not exist in controlled settings anywhere on Earth. The interaction strengths needed to explain 2 solar mass neutron stars with hyperons present exceed what can be independently constrained by any observable other than the neutron. star masses themselves. The fix invokes a force we cannot independently measure to solve a problem produced by forces we can. The second resolution proposes a quark-matter phase transition. At high enough density, nuclear matter dissolves into a plasma of deconfined quarks before hyperons can form, bypassing the softening entirely. This is theoretically viable in some frameworks. It fails to produce a unified equation of state that simultaneously satisfies the nicer mass and radius constraints, the JW170817 tidal deformability limit, and the predictions of perturbative quantum chromodynamics at asymptotically high densities. No quark phase transition model satisfies all three independent constraints simultaneously without introducing adjustable parameters that have no independent motivation. A third approach introduces additional exotic matter, kaon condensates or modified hadronic interactions, to stiffen the equation of state through different mechanisms. Each modification faces the same convergence of simultaneous requirements. The observed masses demand stiffness. The tidal deformability constraint demands some compressibility. And the radius window from NICER is specific enough to eliminate most combinations. No proposed exotic matter model satisfies all windows simultaneously. The densest objects in the observable universe either do not contain what the physics of the strong interaction says they must, or they contain it and exist in a state the equation of state of matter says cannot be stable. Everything before this was located in something, in the chemistry of stars, in a particle signal, in a galaxy, in dense stellar matter. What follows has no object. It is a property distributed across the largest empty spaces in the universe, regions between galaxies where the standard model provides no mechanism for structure to arise. Something arose. The field is there, confirmed across independent instruments and independent analyses. There is no solution date. There is only the measurement, sitting in the void where the equations allow only absence. The large-scale universe is not uniform. Galaxies organize into filaments and walls, separated by vast regions of near emptiness called cosmic voids, volumes spanning tens to hundreds of megaparsecs, where the average. Matter density falls to 10 or 30% of the cosmic mean. These voids are not incidental. They are the structural complement to the filaments, and they account for the majority of the observable universe's total volume. In the standard model, they are cosmologically inert. They contain almost no plasma, almost no conducting medium, and almost no mechanism by which charge carriers can organize into the flows required to generate magnetic fields. The magnetohydrodynamic equations that govern magnetic field evolution across cosmic time produce a specific prediction for voids. Magnetic fields should be absent, below 10 Gauss in the most conservative theoretical frameworks, unmeasurably small, effectively 0. The detection method exploits a specific property of high-energy astrophysics. When TV energy gamma-ray photons from distant blazars, active galactic nuclei with relativistic jets pointed toward Earth, travel across hundreds of megaparsecs of cosmic void. They pair-produce on the extragalactic background light. A photon converts into an electron-positron pair. Those secondary charged particles upscatter lower-energy photons through inverse Compton scattering, producing a cascade of GV energy photons that should be detectable by gamma ray telescopes as an extended halo around the blazar source. The geometry of that cascade, whether it arrives as a narrow beam or a diffuse halo, whether it arrives at all, depends entirely on whether a magnetic field exists in the traversed void. In 2010, Neuronov and Wolf applied this analysis to Fermi-Lat blazar data and found a result the field designates with deliberate understatement as a quiet impossibility. The voids between galaxies contain a magnetic field that standard cosmology has no mechanism to have placed there. Neuronov and Wolf 2010, Science 328, pages 73-75, found that the expected GV cascade emission was absent from the Fermi-Lat data. not suppressed, absent, in the directions of. TV blazars, where it should be detectable if the void magnetic field were effectively zero. The only consistent explanation: a void magnetic field of sufficient strength and coherence length to deflect or delay the secondary cascade below detection. Their derived lower limit, B-10 Gauss over coherence lengths greater than 1 megaparsec. The standard model predicts effectively zero. The observation constrains it to more than 10 Gauss. That is a discrepancy of more than 14 orders of magnitude between the predicted upper bound and the observational lower bound. Subsequent analyses have reinforced the constraint. The MAGIC telescope collaboration, from observations of blazar H1426 plus 428, set lower limits of approximately 310 Gauss over coherence lengths exceeding 1 megaparsec. Veritas and H-ESA's observations of independent high redshift blazars yield consistent lower bounds. Alves Batista et al. 2021. Universe Review document convergence across multiple independent analysis teams and methodologies on a lower limit that no standard cosmological process generates. Zero predicted. More than 10 Gauss confirmed. Consider a sealed room confirmed to have no air pump, no electrical source, no machinery of any kind, sealed, measured, and verified empty. Then take a pressure reading inside and find the pressure is not zero. It is low. But it is not zero, and no known opening or source can account for what is detected. The first explanation invokes primordial magnetic fields generated in the early universe, during inflation, or during phase transitions in the first fractions of a second after. The Big Bang, when quantum fluctuations of a spectator field could in principle generate coherent magnetic seed fields that survive dilution across cosmic expansion. This is theoretically possible in some inflationary models. It fails to reach confirmation because no inflationary model that generates void magnetic fields of the observed amplitude and coherence length is independently motivated by CMB. Data, CMB polarization anisotropies, or any other observable. Every such model has been constructed specifically to produce the result it is then invoked to explain. There is no independent measurement that selects the inflationary parameters required. The second explanation proposes plasma instabilities. The electron-positron cascade produced by the blazar TV photons undergoes beam instabilities in the intergalactic medium, scattering the secondary particles before they can produce detectable GV emission, mimicking the signature of a real void magnetic field without one being present. Observational arguments against this mechanism include the consistency of the lower limit across blazars at different redshifts and in void regions with different physical properties. If plasma instabilities were responsible, the suppression efficiency should vary with environment in detectable ways. The lower bound is consistent across sources spanning different redshifts and sightlines through different void environments. The plasma instability explanation requires identical suppression efficiency in every tested environment with no physical reason for it to be so. A third explanation attributes the signal to residual astrophysical emission, unresolved background sources, or blazar intrinsic extended emission mimicking cascade absorption. Multiple independent groups have modeled the spectral and spatial signatures of cascade emission and applied dedicated foreground subtraction to the Fermi-Lat data around multiple independent blazar populations. The lower bound on void magnetic field strength survives every foreground correction applied across every independent analysis. The largest empty regions of the universe contain a magnetic field that no known astrophysical process and no standard cosmological mechanism could have generated or placed. There, everything before this was a puzzle about specific physics, missing elements, particle crossings, formation timelines, dense matter, fields in empty space. Each entry challenges one prediction in one framework. What follows does not challenge a prediction. It challenges the premise that made all the predictions coherent. It operates across the full observable sky, the entire catalog of distant galaxies and quasars, and asks whether the single foundational assumption underlying every cosmological model ever constructed is valid at the scales we can actually observe. There is no solution date. There is only the gap between the universe we assumed and the universe we can measure. Every calculation in cosmology rests on a premise, not a measurement, a principle. The cosmological principle states that the universe, viewed at sufficiently large scales, is homogeneous and isotropic, the same in all directions, the same in all locations. It is the reason we can build a model of the entire universe from observations made at a single point in space. It is why the cosmic microwave background can be used to derive the baryon density of the universe rather than just the baryon density visible from Earth's position. It is why the Friedmann-Lemaitre-Robertson-Walker metric, the Fluoro framework, can describe the universe as a whole rather than only our local region. Without isotropy at large scales, there is no universal cosmology. There are only local descriptions that cannot be generalized. The cosmological principle is not a parameter. It is the foundation that permits parameters to exist. Our galaxy moves through space. That motion produces a measurable asymmetry in the cosmic microwave background. One direction appears slightly hotter, the opposite slightly cooler, as our velocity creates a Doppler shift in the background radiation. This is the CMB kinematic dipole, corresponding to a velocity of approximately 370 kilometers per second in a specific direction, with a fractional amplitude of roughly 0.007. This motion also creates a testable prediction for the distribution of distant objects across the sky. The direction we move toward should show a slight excess of galaxy and quasar counts, appearing slightly brighter on average. The direction we move away from should show a slight deficit. The predicted amplitude of this source count dipole, derived directly from our measured CMB velocity and the cosmological principle, is approximately 0.007, matching the CMB kinematic dipole. In both direction and magnitude, they should agree. This agreement is a direct instrument-independent test of whether the universe is isotropic at the scales where we observe distant sources. The latest all-sky quasar catalogs, analyzed across multiple independent teams using multiple instruments, have completed that test. The term the field now applies to the result is defiant alignment. The sky points more strongly in one direction than our own motion through the universe can account for. The first robust measurements of the source count dipole in radio surveys, NVERSE, the NRAO-VLA Sky Survey, began suggesting an excess over the kinematic prediction in the 2000s. The definitive modern result arrived through CATWISE, the infrared all-sky survey from the WISE and NEOWISE space telescopes, cataloging over 1 million extragalactic quasar. Sources: Seacrest et al. 2021 measured the quasar dipole in CATWISE and found an amplitude of 0.0155-0.0008, roughly twice the kinematically predicted value of approximately 0.007. The alignment in direction with the CMB kinematic dipole is precise. The amplitude excess is approximately twofold. The combined significance across radio and infrared datasets exceeds 5 sigma. A 2025 review co-authored by Seacrest and published in Reviews of Modern Physics, Volume 97, Article 0411-003/9YGXZ2IQRXIV2505.23526, consolidates the anomaly across CATWISE quasars, NVSIS radio sources, and RAXLO radio data from the Australian SCA Pathfinder telescope, confirming the discrepancy at greater than 5 sigma combined significance. Wagenveld et al. 2025 independently confirm the excess in NVSIS and RAXLO analyses. The anomaly is not in one dataset. It is not from one team. It is present wherever the sky has been measured precisely enough to find it. 2 times the predicted amplitude. 5 sigma. Confirmed independently. Imagine dropping identical pebbles into a perfectly still pond from the center. watching the ripples spread outward uniformly in all directions as the physics of a symmetric surface requires. Then find that 1/2 of the pond's edge consistently receives stronger, more frequent waves, not randomly, but systematically, in a fixed direction, as though the water beneath the surface is shaped along an axis that the surface itself does not reveal. The first explanation is local structure. We may reside within an underdense region, a local void, or participate in a large-scale bulk flow that adds to our motion relative to the CMB rest frame, producing an apparent source dipole larger than the CMB velocity alone predicts. A bulk flow or void large enough to produce a twofold amplitude excess should leave detectable signatures in the three-dimensional peculiar velocity field of nearby galaxies. In kinematic Sunyaev-Zeldovich measurements of galaxy cluster velocities, and in the angular distribution of galaxy counts in intermediate redshift surveys. None of those observations returns evidence of a flow or underdensity consistent with the required amplitude. And any local effect must also reproduce the precise directional alignment between the excess source dipole and the CM kinematic dipole, an alignment that a generic local structure has no reason to maintain. The coincidence required is not physically motivated. The second explanation attributes the excess to survey systematics, incomplete sky coverage near the galactic plane, flux calibration gradients across survey footprints, or source selection biases that preferentially sample one hemisphere over the other. This has been subjected to the most extensive systematic testing in this subfield. Multiple independent groups have applied different masking strategies, different flux cuts, different angular scales, different source redshift distributions, and different analysis frameworks, including forward modeling of the expected dipole and Bayesian inference to the Catwise NURSE and Raxlow data. The excess persists robustly across every systematic test applied by every independent team. The anomaly is not a feature of the analysis, it is in the data. The third explanation modifies cosmological structure directly, anisotropic cosmological models, tilted universe scenarios, or large-scale departures from fluoroisotropy. These can accommodate a preferred direction in the matter distribution in principle. They fail because they must simultaneously preserve the detailed structure of CMB acoustic peaks, which are consistent with standard isotropic cosmology to sub-percent precision. Baryon acoustic oscillation measurements in galaxy surveys, and the type Via supernova Hubble diagram. Every anisotropic model proposed to explain the dipole anomaly introduces new inconsistencies in at least one of these independent conformations of isotropy. No unified framework accommodates the anomaly without creating new tension elsewhere. The foundational assumption that the universe looks the same in all directions at large scales, the cosmological principle, the premise underlying every cosmological model ever constructed, may be invalid at the scales we can actually observe, which means every model built on that assumption inherits an error we cannot currently locate, quantify, or remove. 7 anomalies, all of them confirmed, all of them existing simultaneously in the same universe, measured by the same species within a single century of systematic observation. A deficit in the oldest element our physics predicts. 2 signals arriving from inside the Earth. Particles crossing distances the universe should have blocked. Galaxies too massive for the time available to build them. Matter in the densest objects that cannot coexist with the physics of the densest objects. A magnetic field in a void that no standard process generates. A sky that points in one direction twice as strongly as our own motion can account for. None of these is a rumor. None is a theorized anomaly awaiting measurement. All of them are measurements awaiting a theory. The standard cosmological model, lambda CDM, is the most successful framework our species has produced for describing the universe at large scales. It correctly accounts for the expansion history, the growth of large-scale structure, the temperature fluctuations in the CMB, and the distribution of galaxies across billions of years of cosmic time. That success is real and not in dispute, and it cannot bring all 7 confirmed discrepancies inside its framework simultaneously, not approximately, not with adjustments at the edges. Every modification that resolves one anomaly creates tension in at least one independent observable. The model is not wrong. The universe is consistently producing results the model does not contain. What this means is specific. A species uses the best instruments it has ever built to take the most precise measurements it has ever achieved. The measurements return results outside the predictions of the best theory it has ever constructed. This has happened before. It is how physics has always advanced. But there is a version of this situation that is qualitatively different, when the anomaly is not in a specific regime or a specific object, but in the assumption that makes all regimes and all objects parts of a single coherent model. The cosmological principle is not a parameter. It cannot simply be adjusted. If it fails at observable scales, the corrections are not additive. They are foundational. 7 observations return the same quiet fact. The universe does not fully fit inside our understanding of it. If you return to this thought later, uninvited, that is the appropriate response to what the data currently says.